Ernest and Nushin and Anastasia, but I think Nushin is starting. Take it away. Let's do the workshop. So I think, yes, Nushin has shared her screen. Excellent. Thank you.
Uh, Hello everyone and welcome. Our presentation today is titled The New Stethoscope, LLMs, Multimodal Models, and the Future of Clinical AI. We chose this title very intentionally, much like the original stethoscope. We believe AI is not a tool to replace clinicians, but an essential instrument to augment their senses, helping them see patterns and gain insights they couldn't before. My name is Nushin Jafarpishe, a postdoc at the University of Toronto. I hold a PhD in electrical and computer engineering from Concordia University. My background involves applying AI to health-related problems. We also have Ernest, a postdoc researcher. He holds a PhD in medical science, is an NVIDIA healthcare ambassador, and an instructor with the NVIDIA Deep Learning Institute. He brings a focus on translating AI to practical clinical applications. And we are honored to have Dr. Anastasia Economou, a professor of radiology at the University of Toronto and the division head of cardiothoracic imaging at Stony Brook. She's a staff radiologist and an affiliated scientist whose research focused on using AI to classify and understand lung disease. In this workshop, first I'll cover the theoretical and preliminary concepts in LLMs. Then I hand it over to Ernest for the coding section and Dr. Anastasia for interpretation and discussion of the AI results. So let's start with the basics. What are large language models? You've all heard of tools like ChatGPT. At their core, LLMs are AI systems trained on vast amount of text data with one primary goal, to understand and generate human language. They're built on a groundbreaking architecture called the transformer. The key innovation here is self-attention, a mechanism that lets the model understand context by weighing the importance of different words in a sentence. It enables LLMs to learn long-range dependencies and contextual meaning by allowing each word in a sequence to look at and weigh the importance of every other word. The way they learn in simple terms is by predicting the next word. By doing this billions and billions of times, they do not just memorize text, they learn the underlying statistical patterns, grammar, and even complex concepts. Large language models functions through a complex and systematic process. LLMs are like digital chefs. Think of it this way. Your prompt, the words you type in, are the ingredients. The model chops these words into smaller pieces called tokens. It then mixes them using its knowledge of attention and context and serves up a perfectly seasoned new sentence. It's a process of deconstruction, understanding relationships, and intelligent reconstruction. So, why is this matter for medicine? Because medicine is incredibly language heavy. Think about it. Patient histories, clinical notes, radiology reports, research papers, insurance guidelines, it's all unstructured text. This is where LLMs show their revolutionary potential. They can summarize patient reports. A doctor could get a concise summary of a 200-page patient file in seconds. Another, it generates structured reports. They can listen to a doctor's free text dictation and turn it into a perfectly formatted structured report. Explain findings to patients. They can take a complex medical report and translate it into plain, easy to understand language for a patient. So LLMs can turn massive amounts of unstructured medical data into usable, actionable insight. Building on that, we can see the applications of LLMs span across the entire medical field, which can group into three main pillars: clinical practice, medical education, and medical research. In clinical practice, this goes beyond the report summarization we just talked about. We are seeing tools for medical question answering, handling time consuming administrative tasks to reduce burnout, and even providing data driven support for clinical decision making. In medical education, the potential is transformative. LLMs can create personalized learning paths for students, generate new educational materials and case studies, and even simulate virtual patients for students to practice their diagnostic skills. And finally, in medical research, these tools are accelerating discovery. They can provide assistance with academic writing, help researchers by translating studies from other language, and perform complex data analysis on large data sets. And that evolution involves a specific life cycle. We can't just take a general model like ChatGPT and drop it into a hospital. It needs to be specialized. This happens in three phases. First is training. This is learning from scratch on general data from the entire internet. Fine-tuning. This is where it becomes a specialist. We take the general model and retain it specifically on medical textbook, clinical notes, and research papers. Inference. This is the applying knowledge phase, where the fine-tuned model can now answer new unanswered medical questions, a process that is called zero-shot or few-shot inference. Let's consider your thinking process. When you are presented with a picture by someone who is telling you about something, you don't simply read what they are saying or simply observe the picture. Your brain skillfully integrates the two inputs to form an understanding. This is exactly what multimodal LLMs do. They are capable of processing multiple data types at once. They aim to mimic how humans combine multiple information sources for reasoning. Multimodal LLMs integrate text, images, audio, video, but traditional LLMs process only text. Also, the application of LLMs we talked about so far in medicine are all powerful, but they are still primarily text-based. To become true clinical specialists and handle the full spectrum of medical data, we need multimodal LLMs. A clinician uses all their senses. They look at the patient, they listen, they read the chart, they see the x-ray. So multimodal LLMs, unlike the revolutionary power of AI that can see, hear, and speak. We are moving from AI that only reads text to AI that can perceive and understand different types of data all at once. This is in practice today. These models are being built to integrate and reason about image, text, and other data sources, just like a clinical team does. Multimodal LLMs do not simply load various AI systems on top of each other. They involve complex encoding, alignment, and fusion algorithms. First, in the encoding phase, the model has to perceive the different inputs. It uses one specialized component, like an image encoder, to turn the X-ray into a set of numbers. It uses another component, let's say a text encoder, to turn the patient notes into another set of numbers. Second, which is the core challenge, is the alignment phase. The AI must learn how the numbers representing the image relate to the numbers representing the text. It has to learn that this specific cluster of pixels in the X-ray correspond to the word pneumonia or fracture in the report. Third, in the fusion phase, The model combines or fuses those two aligned streams of information. This increases one single rich data representation that contains both the visual and textual context. And finally, in the processing phase, this single fused input is fed into the large language model, which can now reason across the combined data to answer a complex question or generate a new comprehensive report. So, when we apply multimodal LLMs in healthcare, we are talking about an AI that can look at a chest x-ray, read the radiologist notes, and review the patient's EMR data, all at the same time. However, we must be critical and reasonable. This technology introduces significant challenges. First, privacy and regulation. How do we train models on sensitive patient data while remaining fully compliant with privacy laws? Second, transparency and fairness. We must ensure these models aren't black boxes and that they don't amplify existing bias in our health data. Third is complex integration. How do you actually combine a high resolution image with a dense text report? It's a massive engineering challenge. And finally, and most importantly, we need clinical validation. We cannot deploy these tools until we have proven in clinical trials that they are safe, accurate, and truly beneficial. Let's look at a concrete case study that tackled these challenges. MedGemma. This is a perfect example of a multimodal medical model. If you look at this timeline, you can see the rapid progress. In early 2025, Google released the general purpose open source Gemma models. These models provided the architecture foundation for MedGemma. They were built on research from the Gemini models. In May, MedGemma was officially announced and first released at the Google I/O event. The initial release included MedGemma 4B and MedGemma 27B text only. MedGemma 4B is a 4 billion parameter multimodal model capable of processing image like X-ray and dermatology photos and text. MedGemma 27B text only is a 27 billion parameter model optimized exclusively for medical text comprehension and clinical reasoning tasks. In July 7, the initial MedGemma technical report was submitted to arXiv. The report detailed the model's architecture, training, and performance benchmarks. In July 9, Google released the flagship MedGemma 27B multimodal instruction-tuned model, completing the initial collection. This version integrates image, text, and electronic health record data capabilities, offering the most comprehensive feature set in the family. Let's look at some key features of MedGemma. Medical image analysis. MedGemma 4B can interpret medical scans like X-ray, MRIs, and CT images. It helps radiologists generate detailed reports and identify key findings. Text summarization. MedGemma 27B can take long clinical documents and turn them into concise, easy-to-read summarizes. This saves time for doctors who need quick information. Medical question answering. Both versions can answer questions like what are the symptoms of heart failure or how is asthma treated? This helps doctors, students, and even patients. Open source and flexible. Being open source means you can fine-tune MedGemma with your own medical data to make it even more accurate for specific needs. MedGemma has many potential uses in healthcare. Here are some ways it can help. Radiology reports. MedGemma 4B can generate detailed reports from medical imaging, helping radiologists save time and focus on critical cases. Clinical summaries. MedGemma 27B can process long patient records and create summaries, making it easier for doctors to get key information fast. Medical education. MedGemma's question answering features make it a helpful tool for teaching students and training new healthcare professionals. Healthcare apps. Developers can build apps that integrate MedGemma's features supporting telehealth, patient monitoring, and decision support systems. This brings us back to our challenge of clinical validation. We need a grand truth. For this workshop, we used an example from this reference dataset, book Interpreting Chest X-ray illustrated with 100 cases. In addition to this book, we also have a set of X-ray provided by Dr. Anastasia. As the slide says, this book contains 100 real clinical cases with questions, the chest X-rays, and most importantly, the expert radiologic impressions. We then use this expert explanation as our gold standard reference. We fed the X-ray and the question to MedGemma, and we evaluate its X-ray output for accuracy and completeness against the book's answer. This allows us to systematically compare the model's interpretation with the expert findings to determine its clinical correctness and, just as importantly, find its weakness and areas for improvement supported by also clinical knowledge of Dr. Anastasia. So we have covered the full journey. We started with the basics of LLMs and their broad application in medicine. We saw how they are evolving into powerful multimodal models that can see and read. And we've just walked through a real world case study, MedGem, and shown a concrete method for how we are working to validate it. Now that you have the theory, it's time for practice. I'll now hand it over to Ernest, who will walk you through the coding part, and Dr. Anastasia for interpretation and discussion of the AI results. But before we move forward, we have, I think, about 5 minutes for Q&A. So I'll be happy to take any questions. Thank you.
Thank you, Nujeen. Does anybody have any questions before? Oh, Jeff has a question. Please go ahead. Can you unmute yourself, Jeff?
So I can unmute
Oh,
this.
yeah. There you are.
I'm even going to turn on my camera for a second.
Yes.
That was a great talk. Thank you very much for that. And I actually didn't know that MedGemma 27B is available. So my question is, for those of us who don't have good hardware to run it on, do you know if it's hosted somewhere in the cloud if you want to do experimentation with it?
Yeah, so MedGemma parts, Ernest will talk about it more later. But actually, what we can certainly know that the archive from the MedGemma that contains like the how about training and this stuff are available, but in order to get the weights and exactly what they have done, it needs some like some permission and ethical exchange and this stuff. So we cannot say it's fully publicly available and open source in that means, but it's possible to get the weights by some like institutional agreements.
Okay, thank you.
I can make some more comments on this. So of course there are some agreements. It's not hard to do. Google is doing a great job with open sourcing their models. The consideration for computational resources is is not unique to anyone. There has been a lot of discussion in the research community, as you know. So there are many, many different ways. There are companies that give you resources on demand. For example, Lambda is one of them. So you can rent some online GPUs, even Google Colab. We're gonna use it today. I'm gonna go for the 4B model, but with a premium edition of Google Colab, you can even run the models there. Another way that if you have a I wouldn't say high-end GPU these days, but with a decent GPU, another option you have to run the models locally is that you can go for quantization. So they cut off some of the precisions in the weights of the models, and in that case, the models become lightweight and then you can run them locally. Given all the concerns we have in Canada and healthcare for patient privacy, this is another option.
Yeah, thanks. My hardware, so I can run a 4 billion parameter model, no problem. But even with quantization, I'm still too poor to have hardware good enough to run a quantized 27B model. So, but that's really, I appreciate that. I'm going to see if I can find it hosted somewhere or somewhere that I can download the weights to, like Lambda or even GCP maybe.
Sure.
Thank you.
All right, we have a question in the chat, and it's from Mabiha, if I'm pronouncing your name properly, I hope. Hi, I'm an undergraduate student at the University of Toronto. I was wondering if MedGemma moved to the clinical trial stage yet, or when do we expect to see it in that stage if it is not there already?
Um,
Who would
yeah,
like to
so
tackle that one?
so Ernest, correct me if I'm wrong, but I think it needs more clinical validation to become fully adapted to a clinical to the real world, because as we see in the next part, we can see that maybe there are some differences between the what the model says and what's the actually what's a real radiologist can actually comment on that. So it needs actually, I think, more time because it hasn't passed many times that it has just released. So for sure, it needs more clinical validation.
Yeah, and
Uh,
I think we can have a great discussion on this at the end with Dr. Oikonomou's insight because this is an open question. Of course, there have been many papers published with MedGemma, even though it's relatively new. But clinical trial, I haven't heard anything. Another big question is how to use these models eventually in clinical settings, because what computer scientists expect and design the models with those expectations can be different from what we need in the clinical setting.
So I can jump in as well. Just it's a great question, by the way. Thank you. Just for clarification, the MedGemma is the open model, and the reason they release it is because they want to accelerate innovation. So meaning, all of you after this wonderful workshop will want to play with MedGemma. But the model, it's based on a research model called MedGemini. No surprise. And that's the research model that's locked down and is not available openly. So if the model were to ever go to clinical trial, it would be the MedGemini model that would go to it. It wouldn't be the open source model. And then it would go through clinical trial, and then it would be released, as a product, essentially. So to answer your question directly, no, I don't believe it has. Are they currently in the process of trying to get it to go through regulatory processes? Maybe, but I would guess it's still pretty early. So to my knowledge, no. And don't expect MedGemma to ever become or go through that process. It will be MedGemini or a version of MedGemini that will progress from a research model, which is what MedGemini is, to a clinical model, like a clinical application product model that would go and be locked down for production and release through regulatory, right? So don't forget, all models, if they're released, have to be locked down. So meaning no change anymore until a new version that has to be assessed and validated before release again. Okay. Hopefully that answered your question. Any other questions before we move on to the fun of the workshop? Great. Let's get going because we're actually a little bit behind. So
Awesome.
take it away, Ernest. Thank you very much.
Great. So I put the link in the chat. We have a GitHub repository for this workshop. On the repo, you already have access to the codes, data, presentation, and also the results. If you go into the codes, we have only one long Jupyter notebook file. For the data, we will have two cohorts of patients. We have DICOM files from 4 different patients, kindly shared by Dr. Oikonomo, and then we have some patients in the format of JPEG, and these are from the book that Nushin mentioned. To run the model, I could use my own resources, but I thought putting it on Google Colab would make it even better for you because you can just replicate what we're doing here. So same directory structures there. I'm gonna open the Jupyter notebook we have, and then let's get started. All right, so the first step in developing any AI pipeline is designing a well-structured file and directory organization. There are multiple valid approaches, and none of them is universally the best. What really matters is to maintain consistency. So pay attention to all the details in your projects. And if you're advanced, you already know all these things. This part is just for those who are not that much advanced in programming and AI research. So file names, folder names, formats, every single detail matters. Even if you use dash or underscore or spaces. So first, we just mount the Google Drive, and then we change the directory to our code directory. So this one. So now our working directory is here. And then we just walk over the contents to ensure that we have access to all the files and etc. So the root directory is this one, ImpactMed 2025. And then we have the structures of the files that we just saw through the web interface. Okay, so if you look at what we have here for two of the patients from the DICOM repository, we have two DICOM files. And for another two, we have only one DICOM file. So that's an example of inconsistency. And then in terms of designing the pipeline, we need to take into account all these small things. So if you want to just use MedGemma or any other multimodal model for getting inference on specific cases, in terms of the research design, when you want to publish a paper, it will be a case report. So in that case, you're fine because it's just a case report. Who cares? You get two different inferences. You can even manually change the file names and report your cases. However, if you want to go for like 400 patients, this becomes tedious and even impossible. So in that case, you need to have absolutely perfect consistency. So if you look at the JPEG repository here, for each patient, we have apps exactly 4 files. The names are exactly the same. So we have something which is called img.jpg. That's the main image file. And then there is question.txt and impression.txt. Impression comes from the radiologist. So it's kind of like a ground truth. Question is what we are asking from the model. And then we have a support image that at least initially you don't need to use it. However, later you can have more advanced pipelines. So that's what we have. A couple of other things. You can just use your API keys because for this workshop, we are pulling the model through Hugging Face. That's another platform that hosts open models, including MedGemma. And you can put your plain passwords there. It's less secure, especially if you're gonna share your codes. So what you can do is that on the left, if you see there is a secrets tab, and if you open the secrets tab, you can choose a name. I'm using HF token, which stands for Hugging Face token, and then put the value. And in this regard, everything is much more secure. And in this cell, we are trying to just approve that we do have access to the Hugging Face. Now, there is another technical note about the family of MedGel model. Nushin briefly covered it. So we have 4 billion parameter and 27 billion parameters model. There is MedSiglib that's specifically trained for image classification. That's a bit different. But within the groups of 4B and 27B, based on the file names, you see PT, which stands for pre-trained, and also IT, which is fine-tuned after pre-training for instruction-based interactions. So if you want to do some sort of question answering, the IT model is going to work better for you. The one that has text, which is only one from the 27B group, that's a uni model. That's just as an input, it accepts text, and as an output, it gives you text. Last thing, through notebook settings. So if you go to edit, and then if you go to notebook settings, you can access some levels of GPU. So if you go on CPU, the models would still work. It will take much longer for you to run the models. With T4, which comes for free, you get access to basic stuffs, and that's what we have for this workshop. You can also pay, and then these other options get all unlocked, and then you have a higher bandwidth for your models, and also you're not that limited in terms of time. Okay, some notes I left on the notebook for you to review later. I'm going a bit faster because I want to have more time for the clinical discussion and also Q&A. Also, if we have advanced programmers, I don't want to make it that boring for them. At the same time, I want to cover the basics for those who do not have enough experience. Okay, so another thing is that you need to get access to the secrets, to the passwords that you save. So using the OS package and then setting environment variables, you can do that. And then we check if the code is running on Google Colab or else. Well, the else I'm just passing. However, if you want to run these codes on your local machines, that's where you need to put some checkpoints and print statements. We need a couple of libraries that are not installed by default on Google Colab. For those who are already familiar with the idea of Jupyter Notebooks and especially Google Colab, you know that if you put exclamation mark at the beginning of something, you get access to the shell of Google Colab, and that's how you can install different libraries that you need. Transformers is one of the most important ones, Accelerate, etc., etc. So you install all these things, and then we start just loading the models. Okay. So nice thing about Google Colab and Jupyter Notebooks is that it gives you some minimal versions of widgets built into the notebook. So if you look at the codes on the left and look at the options I have here, if I go for BPT, this model choice automatically is changed. Now you can do it using the codes. Of course, you can put the text here, or you can just select the model using this widget. Now, as I said, our focus is going to be on 4B version and then the interactive. Okay, so we have the model, and the rest is just loading the model. From Transformers, which is a very famous library backed by Hugging Face, you import the pipeline. And now we are building the pipeline through calling the correct model ID and then the needed arguments that we just defined. So if you do that, if you run this, I'm not running any codes here. I've done that before, and you already see the outputs here after the code cells, because I wanted to save time. But if you do that, depending on the bandwidth of your internet system, that temporal load of the servers, etc., it takes some time. But essentially, at this point, everything you need is going to be downloaded from Hugging Face to your Google Colab. And if you do it, you will see that there will be another folder added here. That's the way we wrote the codes. And it puts the checkpoints for the models, the train weights, etc., etc. So this is where we load the model. The model is loaded, and now we need to load our data. First, we work with the DICOM files. PyDICOM is a famous library for working with DICOM files in Python. So first, you need to install it. Again, exclamation mark pip, the standard package installer for Python, install, and then PyDICOM. You install it. Now I'm defining the model names manually because, as you saw, it was not consistent. For some patients, we had two. For other two, we had just one DICOM file. If it was consistent, or even if it is not, you can come up with some ideas. You can say, hey, just iterate over every single patient directory and one by one load every single DICOM file I have. So that would be a workaround. Anyways, so here I'm hard coding all the file names, DICOM file names. And so now we have access to all these in the form of PyDICOM objects. So ID4 slash underscore image1 is a PyDICOM object from that specific DICOM file for that patient. Now we need to start the analysis. For that, we need some helper functions. So the first one, I call it analyze DICOM with MedGemma. Okay, so we're gonna pass our DICOM objects, which are gonna be these guys, ID2 image 1, ID3 image 1 or image 2, etc. The pipeline, and then some other controls that we will discuss later. So when you do this, depends on your preferences and the design of your pipeline. What we suggest is that always try to get some visuals. Just visually check what is going on with the images, ensure that the file was read correctly, and you need to use all these controls as manual checks. Then we get the image, and when I say we get the image, we have the PyDICOM object. It includes DICOM tags as well as the image array. So with in this line, we get the image array and put it into image. Then we have something called prompt. If you have a little bit of knowledge about large language models, and if you have worked with ChatGPT a bit advanced, you've for sure heard this term prompt. Think about it as a text that you give to the large language model or your multimodal model. So it is very important to format this direction correctly, and itself can be a full day workshop. There is prompt engineering techniques, a lot of them. Uh, Rule of thumb, if you can somehow direct the models in a logical way, there's a technique called chain of thought, for example. If you can direct the models using those logical structures, you get better outputs. Now, this logic can be formed based on the clinical expertise. So if you are a radiologist, for sure the prompt you can write will be better than the one that I would write because you have the domain knowledge and you can provide better information to these LLMs. The only thing you need to know is that these LLMs or multimodal models are a bit different from us. So try to break down the process for them and guide them somehow in a logical way. Another thing which is very effective is that if you can give them some examples. With multimodal, it's a bit more challenging. With limited size datasets, it's a bit more challenging. But we do that with ChatGPT. Even if you don't know the term, you do one shot or a few shot prompting, which means you ask your question and then you say, for example, this is one desired output that I would get. So that, for example, helps a lot. Then you have another part of payload for your prompt. So messages, some of these models need to know some roles. Some they don't need to know the roles. You don't have to describe a scenario that, hey, you are a board certified radiologist. For some models, you do not need to do that. For some, you have to, but it is always a good idea to include all these details because it helps the model to get started and be more direct to the point. And then we have the content. So we have the image, which was loaded, and then we also have the text, so the prompt. Okay, so that's what we are feeding into the model. And the rest is just calling the pipeline, the whole pipeline, using the message, using the image. And then there are some controls. Uh, this is another thing that depends on some decisive factors yet that are out of your control or not directly under your control. For example, this number of tokens. It means how many, for example, if this is just a unimodal model, model, and this is just text only input, how many words? Uh, well, technically it's a bit different, but roughly, how many words are you gonna input to your model? And it depends on the amount of computational resource which is available to you. If you have a small model, but if you use a very large and heavy input to the model, you get hardware failure or memory errors. So you need to play around with these hyperparameters and settings, but that's the idea. And lastly, you get the output in this out, and you format it to a parsable text, and you return it. So this text is something that comes out of your function, and as the input, you saw what we did. We just input the DICOM object. That's not the only part of the input. We also have the prompt, but this prompt in this design, I'm assuming the prompt is always the same. Again, use your imagination. It's not hard to imagine that there are cases that you want to have per case prompt. So a prompt, the directions that I would want to give for one patient is going to be different from the other one. In that case, instead of hard coding the prompt here, you could load this from a text file somewhere, and that text file could be in one of the patient directories. The rest is just formatting the output to get a better a better structured output from the model. You will see what we mean. Okay, done with the technical part for at least the DICOM repository. Let me just go through what we have from for the first case. So ID1, chest X-ray 1. I'm just calling the function we went over, and I'm storing the output of the model into this case report variable. Okay, so this is the chest X-ray we have, and we get the output as part of the analyzing function, because we are printing the text here. However, you saw that we wrote another function to format this. So initial output is this. It's a bit hard to follow. Now, to get it better, we formatted using format case report, and now this is what we get. It's the time for me to stop and ask Dr. Anastasia to jump in and comment on some of the outputs that we got for this specific patient.
Yeah, Ernest, this is only the lateral of the case. There is also a
Yes.
frontal one.
Yes. So
Do we see them separately, or?
we see them separately. So for this lateral, we get one output, and then for the other view, we get another output.
So is there a possibility that we get a combined output, because this belongs to one patient?
Exactly. This is a fantastic point. It depends on the design. With this design, we have two separate reports. Now, there would be different ways. One way would be to input both images at the same time if the model supports, if the memory supports all those things. The other way would be to get these two reports and then give to a text-only model and say, hey, merge these two. Now, if you prefer, we can go to one of the cases that have only one view and then see what we have there.
No, it's like whatever you want. It's just that for a radiologist, for example, to assess the case which has a frontal and a lateral and understand what's going on, has more information, and it's probably unfair for the model to give them only one view at a time and expect to have the same critical thinking that the radiologist would have by seeing both at the same time. Like, it is as if you hide some information from me that I'm a radiologist. There are many cases in real life that we have only a frontal. Almost never do we have only a lateral. The lateral is an addition to the frontal. And when we have two views, frontal and lateral, we're always happier because we have more information. But when we don't have the lateral, it's okay, that's life. That's what we have. Lateral only is almost never happening.
Mhm.
Yeah,
Great
so
points.
whatever you want.
So would you like to go over the second case? We have only the frontal view.
Okay, sure.
So this is the chest X-ray we have, and then you can read the report here.
So it says lungs and pleura. The lungs appear clear without evidence of consolidation, edema, effusion, or pneumothorax. Cardiomediastinal, the heart size is within normal limits. The mediastinal is unremarkable. Bones, soft tissues, no acute fractures are identified. There are no lines. Normal chest radiograph, no acute cardiopulmonary pathology is evident. Yes, I totally agree. When I see this frontal chest X-ray only, I would consider it completely normal. I see the heart silhouette very good on the right side. On the left side, I see the pulmonary hyla. I don't see any consolidation or masses in the lung parenchyma on the right or the left side. The pleural spaces are very clear, very acute costophrenic angles. I don't see any lucency for pneumothorax. The osseous lesions are radiographically completely normal. The upper abdomen is completely normal. The gastric bubble is where it should be, no free air. So I would definitely consider this a normal. So it's completely correct.
Okay. Is there anything that you would say you would add to this report? Is there any part that the model is not doing an excellent job?
No, I think maybe I would not even include the lines and devices. Like, I would only include a comment if there is one. If there is not one, I would not necessarily say there is none. But other than that, it seems very close to the template that we populate each time we want to report a normal. We're not gonna dictate a normal from the beginning. I have a normal template. I just add it and it saves me time. So it looks very similar to what I use.
Awesome. I think case 3 is again one of those cases that we have two views from it.
Yeah.
So let's go to the last case, which is case 4. This is the X-ray, and this is the report.
Yeah. So a comment for this chest X-ray. Probably it is a little bit blurry. The windowing is not ideal, so it looks more gray than it should. And I'm not sure if you can see and distinguish very well some fluffy opacities which are symmetrical in both lung fields, and they look like small flames, as if there are some dirty areas close to the periphery, not close to the heart, but more close to the periphery. So these are the findings that we have. Other than that, the heart is normal and the pleural spaces are clear. Can I see what the AI said? Yeah. The radiograph shows diffuse bilateral interstitial infiltrates, most prominent in the lung fields. The heart size is normal. The mediastinum is unremarkable. The body structures are intact. So diffuse bilateral interstitial infiltrates, I wouldn't say that they are diffuse. They are more close to the periphery. When it says most prominent in the lung fields, I don't think it is correct, because the infiltrates, or like the interstitial infiltrates, would be in the lungs anyway. They wouldn't be in the heart or in the bones. Okay, so when we're talking about infiltrates, also infiltrates is no longer a good term. It has been discarded. So we should talk about opacities, airspace opacities, or interstitial opacities. I would say interstitial opacities more in this case. Then the heart size is normal. Yes, I agree. The mediastinum is unremarkable. I agree. The bony structures are intact. I agree. Again, no devices, no lines. So now the differential diagnosis, it says pneumonia. The diffuse interstitial infiltrates are highly suggestive of pneumonia. So diffuse, we said it's not very correct. Infiltrates, I would not use it. I would say the interstitial peripheral opacities are suggestive of viral pneumonia. When we say pneumonia, we mean more bacterial pneumonia, which is more focal. But when we're talking about interstitial opacities, then immediately the differential diagnosis, the top differential diagnosis is viral pneumonia, something like COVID. Actually, this is a case of COVID, and it is a textbook case for COVID viral pneumonia. So acute ARDS, the pattern could be consistent with ARDS, especially if there is a history of acute illness or trauma. Yeah, a little bit stretched. With ARDS, you want really diffuse airspace opacification of both lungs. This is more in the periphery and more interstitial opacities. A patient who has ARDS is a patient who is intubated. There is no endotracheal tube, so the patient is clinically not in such a severe condition. So I would put ARDS very much at the bottom. I would not even consider it, I think. Pulmonary edema, although less likely given the interstitial pattern, I agree. Pulmonary edema should be considered, especially in the setting of heart failure or other cardiac conditions. I agree. Interstitial opacities, however, should be more central. These are peripheral, and we don't have cardiomegaly. So yes, on its own, interstitial pattern should be considered in pulmonary edema, but there are other things that do not make us happy with this diagnosis. There's no cardiomegaly, and it's more peripheral than central. About aspiration pneumonia can present with similar infiltrates. Yes, I would take that, but I would not use interstitial infiltrates. I would use airspace opacities. Viral pneumonia, we've already discussed about it. Definitely, it is the best diagnosis. I agree. And fungal pneumonia, certain fungal infections can cause interstitial infiltrates. I would take this as correct as well. However, most commonly, it's not interstitial pattern, it is nodular pattern that we see in fungal pneumonia.
Awesome, awesome. I love this. It's becoming like a panel. I need to go back to the recordings and then maybe use the transcripts because I've been using MedGemma for other projects, and I know in other modalities it can be even more off. So I would say X-ray is one of its strengths. And based on what you mentioned, correct me if I'm wrong, but I think it's good, but it's not perfect. There is room for improvement in many cases. Now, one question that I have from you is that let's say you're in a clinical setting, you need to report some cases, and there is just one front of you for that case. Let's say this is the case. Uh, if you are provided with this report, as the starting point, would it help you and lighten some of your work, or would you prefer to start from scratch and write your own report?
I think based on these specific reports that I got, I would easily correct it much faster rather than going from scratch and use my own.
Okay.
I am not at 100% happy with the reports, but I am probably 70% happy. So I think I would it would take me much less time to correct them.
Awesome. Awesome. And I have one more question, if I may.
Sure.
So there are other pipelines. Now, with this setting, what we are doing is that we are giving one text some instructions and then the image and say, what do you think? And we get a report. However, there are other pipelines that are like end-to-end pipelines for some sort of classification. Let's say pneumonia versus COVID versus normal classification. I can ask the model in the prompt and say, hey, as the output, only give me these three numbers: 0 if it is normal, 1 if it is COVID, 2 if it is pneumonia. Technically, that's another story. I will add some comments at the end for those scenarios. But based on the report that you see, these are the insights of the model. Would you trust or would you think that that pipeline would be a reliable pipeline? Or uh, as the explainable AI module, you would like to have a model which is way more sophisticated and takes into account more variables and findings, and then do something else with it?
Sorry, maybe I didn't understand very well. Like, this would be in a scenario that I would be given only a cohort of patients with normal COVID and pneumonia, or there could be like other infections or lung cancer or ARDS, and then I would be asked to use only a pipeline of these three options.
So what I'm trying to say is that let's say there is a scenario when this pipeline becomes a black box. There's no report. It's just one number. Would you trust it? It just says
Again,
this is normal. This is
where would I have to apply it for?
that's a great question. Again, up to you. Maybe as the beginning, it's just for research.
No, I know, I understand that, but would I have, by using this pipeline, would I have to make a diagnosis for a known population or patients who are known to have either normal, either COVID or pneumonia? Or would it be an unknown cohort of patients that could have everything? If this is the case, then I would not feel confident using this pipeline that would have only these three options. I would definitely miss other options, other diagnoses. But if you tell me, okay, I'm giving you 300 patients, and these 300 patients, there are some normal, there are some COVID, there are some pneumonias, we don't know which one is which, and then we have this pipeline, yes, I would use it because it has only these three options.
Okay, that's interesting. Thank you very much. Thank you. Okay,
Ernest,
sure.
do you mind if I jump in and ask a question here? Because all of this has been very interesting. And you brought up at the beginning the few shot prompt, right? So, meaning the ability to prompt per input, correct? And so I'll ask you, and then I'll ask Anastasia as well what she thinks. So, if you do have two images, Anastasia is absolutely correct. It's a shame that the model is not going to interpret the two images together and learn the relationship between the two images, which is what Anastasia is alluding to when she says when she works as a radiologist, she wants to see both at the same time to make decisions. So potentially we could concatenate the images. So if patients have two images, you can concatenate them into one, and then you could do a few shot prompt and say, hey, by the way, this one is two views of the same patient. Please interpret at the same time. So that's my first question. Would that work well to be able to do that? And then the second question is, Anastasia has pointed out repeatedly that she has a personal preference, and it may actually be, from her department as well, and in how she reports in terms of terminology, description, the use of language, the way she reports, so once again, without having the need of fine tuning, which you could do as well, but then you would have to retrain on your own data set. She could, or you could put for her a few shot prompt that would accompany all inputs, and that would describe, it would say, my preferences as Anastasia is to use this, this, and this, and to report in this order, and please use this terminology. What do you think of that?
Absolutely, yes. Those are all great points. Um, Again, confession, it's the design that I implemented, which becomes limiting here. However, MedGemma does have the option, and I've used that for even multi-view videos. And you can provide the model with like two different videos. There are ways for that. Regarding the style, few shot helps. You can also have a post-processing pipeline which uses another large language model to say, hey, these are like 1,000 different reports that I wrote before. Learn the style of the writing and apply it to this new one. So
Amazing.
keep the contents of the output the same. Don't add anything. Don't inject any new information. Don't remove anything. Just in terms of terminology, use my language. That's also possible with FewShot. It improves it to some extent. However, because of the uh, heavy training of the base model, even with FewShot, you cannot really change completely the style of reporting. Yes, sections, different sections, yes, but terminologies and terms used, it's a bit harder in my experience. But those are all great points and very crucial for designing all these pipelines.
Amazing. Amazing. Thank you.
Great. So we move to the last part quickly. And as I said, I would like to dedicate more time to Q&A. Same idea we have here. However, we do have consistency. So some helper functions and what we have at the end is a pipeline that can go over every single patient directory using this load patient and return uh, anything that we saw in the data set. So patient directory, of course, it's just a directory address, but question text, you saw we had a dedicated file for that, impression text, and then the image, and then the support image, and also some auxiliary um, intermediary inputs. Okay, so if you do this and for this pipeline, uh, the one thing which is a bit different from what we had before is this question.txt. So it it is the case that now the prompt is different for every single patient. So we read this text file and we put that into the prompt. Impression, we don't use it at all. It's just for acting like a ground truth for us. So that's the idea. The rest is just going over the directories and load the files and do all those things. We use the same model, we use the same pipeline. So here I'm just loading one of the patients. It's the first patient. Okay. So here we get the patient lists and then we load the first patient data. So the question is that a 35-year-old male presented with fever, cough, and purulent platum. When you're not a doctor, why do you even try to read these things? I don't know. For 1 week, this was his chest X-ray. What is the diagnosis? And then the impression is what is provided in the textbook for us based on the insight from radiologists. Okay, so this is the chest X-ray. And then after in the book, they provide us with a support image to provide some further explanations on this support image. And the rest is the same. We just get the inference. However, instead of printing it here and checking what is going on, we save everything because this is a data set. So the idea is that we're gonna use this over tons of different patients. Yes, it's true that here I only have 3 patients, but if it was 3,000, it wouldn't change anything for me. Now, going to the results, for each patient, we will have one text file, and each text file includes the output from the patient. As you can see, it is not post-processed yet. So then you will need to write other functions to post-process this output. Um, However, you can still look at the outputs and see what the model thought about this case. So again, Dr. Anastasia, could you comment on our first patient? So this patient.
You want me to comment on what I see on this chest X-ray, or should I read what the AI said?
Well, perhaps quickly give
What I
us some
think.
insights and then we go to the
Yeah.
outputs.
Okay, so first of all, it's technically it's not a good image, at least. It's very black, overexposed probably, or it is the way we see it from the book, because I understand that you took this image from the book, right?
Yes.
Yeah, anyway, so we can see that the cardiomediastinal silhouette looks good, but there is definite opacity. There is an airspace opacity in the right lung base. So when you see the image, the right of the patient is to your left. So in the right lung base, there is an airspace opacity, which is very, it's suspicious for a pneumonia. There may also be small right pleural space. I don't have a lateral to confirm. The rest, like the left lung and the pleural space, looks good. I cannot exclude pneumothorax, which looks black on a chest X-ray, just because the X-ray is very black on its own. So I'm very resistant. I don't feel well commenting about pneumothorax, and the rest, like the bones look good and the abdomen looks good as well. So I would say there is a pneumonia in the right lung base. Follow up chest X-ray after 4 to 6 weeks. After appropriate medication is recommended in order to improve, to see improvement or resolution.
Awesome. So I think the model is telling
Pretty
us,
good. It's pretty good.
yeah.
Yeah. Okay, I agree with most of it. I just said that I have some hesitation about the pleural effusion. It's because I don't have the lateral, and the pneumothorax because of the technical problems that we encounter in this chest X-ray.
Awesome. Okay, so we can stop here and go for Q&A, or we can go through other cases we have. I would say we can stop here and go for Q&A. But one thing that you mentioned, and I would like to echo, was the windowing and pre-processing the image. So we do know that clinically it's very important, and one of the attendees can take lead in this research. You can play around with the windowing setting for the input image, and then see how the model's output is changed, whether it is on just one patient or a cohort of patients. And that itself can be a very interesting piece of research, especially because MedGemma is relatively new. I know there are many groups, at least I'm in contact with two of them, who are trying to benchmark this model and uncover maybe weaknesses and strengths of the pipeline. Okay, so I'm gonna stop sharing and then see if there is any questions.
Actually, at this point, I can actually make a little comment on what you just said, which is great. And that is, playing around with the windowing. So the challenges with training these models is that, what's the input that was used to train it, right? So you can imagine that the repositories of images tend to be, uh, good images, right? So images that have been retrieved that are diagnostic quality, right? And so what you're saying is, which is interesting, is that if you play with the windowing, you can actually get the algorithm to learn more from the various windows, which means brightness and contrast, by the way, for those of you that are not radiologists, and then would provide robustness to the model, right? And it's interesting that we observe that. I do a lot of work in ultrasound, and in ultrasound, it's exactly the same thing. It's a huge problem, right? And even more so in ultrasound because it's very operator dependent, and you typically get 15, let's say 5, 15, 20 2D images for B mode ultrasound, and then from the technician or the sonographer, and then you pick the ones that are best in order to make the diagnosis. And it's interesting, we've tried that. So when you do train, if you do train the model with multi-instance learning or something like that, where you have multiple images that are being used for the same diagnosis, so the diagnosis is there. It is interesting that the algorithm does learn that. So you can actually increase the robustness of what you're learning, so that it can tolerate, to an extent, of course, that if your windowing is off a little bit, it will still learn, which is very interesting. So but a very, very good point. Very good point. And I think what you've also shown today, which is fantastic, is that Anastasia is still going to have a job. I love, because everyone thinks, oh, it's going to be so easy to replace the radiologist, but I really don't believe it. And the other thing too is, what we're showing now is quite, you know, common, obvious, like pneumonia, COVID, right? I mean, that's chest X-ray, right? It's very basic. So you can imagine with other modalities, which are even more complex, that it's going to be even harder to just cut out the radiologist, right? I think we're getting close. I think it's wonderful, but I think it really is going to remain a tool for a long time to come. That's my opinion anyway. So, but thank you. We do have a question in the chat. And it's from Nabiha again. Thank you. I'm not too familiar with programming, but I wanted to ask what the feasibility is from a computational perspective when using multimodal LLM to simultaneously take multiple inputs, so frontal, lateral, X-ray, to make a compiled report rather than the separate ones. So I think we addressed that a little bit before, but maybe you can reiterate that, Ernest.
Definitely. Thank you for the question, Nabia. As we discussed, it is doable. And how about this? I can add a block to the codes that include this multi-view input as well. Um, in real world projects, let's say you're working with multi-sequence MRI, because X-ray, it is a 2D image, so it's not memory hungry. But with multi-sequence MRI, you need to have a considerable amount of memory, and that becomes a bottleneck. So then there are different ways to do it. There are tons of technical approaches for doing that. As I mentioned, one way in that case, if you cannot tolerate the computational load, is to get the inference per input, for example, MRI sequence, and then use another, preferably in that case, you should use a reasoning model and provide some more context to say, hey, due to some memory issues, I could not have a true multi-sequence pipeline. However, I'm just fusing different sequences through you, and now just combine these reports. So that would be one way. But for this specific case, for the X-rays, it is doable. Even on Google Colab, it is doable. I'll add one block to the codes, and you will have them on our GitHub repository. Please check it again in a few days. To follow up, what that alter the efficiency of the algorithm that is being used, or would that not be a concern? Well, the efficiency of algorithm, what we expect, and I believe that will be the case, is that it will be improved because, as Dr. Anastasia mentioned, it's unfair to the model to be blinded to half of the information that we could provide to it. So I believe if we have a multi-view pipeline, the efficiency and the performance level will be improved. However, there are some cases. These days, I'm working with echocardiograms as well. And with echocardiograms, my uh, experience is that, of course, the level of noise is insane, and it is video, so memory intensive tasks. However, in some cases, you can distract the model as well. It is counterintuitive to some of the cardiologists that I work with. However, that can happen. It's just because the models are not mature yet. As I said, MedGemma is amazing with some modalities. For X-ray, for sure, it's one of its strength. You saw it today. But with other modalities, if it was not part of its training, it makes a lot of mistakes.
Okay, we have a question from Mohammed in the question and answer box. We're multitasking today. Why would you prepare an RGB image for input? That's the first question. The second one is, can fetal MRI images be used as input to the model? Given that fetal MRI is more complex compared to other MRIs, how does this affect the model's performance or X-ray images?
Thank you for the question. So, RGB images are common in computer science work. There are huge X-ray open source data sets that come in the form of RGB. For the JPEG files that I showed it to you, they were just screenshots from a textbook. But other than that, there is no reason. If you're in a clinical setting and if you are connected to the PACS, what you work with is likely going to be DICOM, and there is no reason to convert it to RGB or any other format. DICOM is a single channel for X-rays at least, and there's no reason to convert it. For the second part of the question, I do not know what will happen to the output for sure. Technically, it's doable. You can test it. And you need to benchmark the model. You need to curate a data set and see how it works. My intuition is that those complex modalities were not part of MedGemma's training, or the model is not that strong on them. So I don't expect you to get great answers for echocardiograms. I can tell you, especially for stress echo, which is a bit rare, transthoracic is more available online, but stress echo is rare. And the answers I got out of the pipeline were almost all off. Nonsense answers were common. So just be careful, but you can curate a small validation data set. It can be just 20 patients, and then you can see what will happen.
I'd also add, I believe MedGemma is 2D, is 2D natively, correct?
You can input 3D as well. There are some approaches you can because it accepts multiple 2D images. So for example, if you have a video, you can go for frame by frame. If you have 3D, you can provide three different views from the image. So it is doable. And I know there are other groups that are working intensively to provide uh, modality specific multimodal models like for just brain MRI. They're doing that. And over time, I'm sure we get better models. The next version of MedGemma, if there is something out, it will be much better than this. If there is no other questions, I would like to add one quick technical comment. We briefly talked about this idea that sometimes you want to create, for example, classification pipelines. In that case, your prompt is going to be, hey, give me 0, 1, or 2 as the output, exactly this, don't do anything else. And then when you get the outputs, because these are based on large language models, sometimes it does not strictly follow your instructions. Sometimes you say, hey, don't give me anything else, just 0, 1, or 2. And still it says, okay, I'm giving you 0, 1, or 2. No matter what you do, there is always some deviations from the instructions that you have. So for that, there are so many different tools. Of course, as you can imagine, you can post-process the outputs. However, there are libraries. LangChain is trying to organize the whole prompting and then the output parsing pipelines. There is another one called Pydantic. It's amazing. There is another way that you can use another LLM for the output to reconstruct and reformat it the way you want. It's always a challenge, and even if you pay for the most advanced models, for the latest version of reasoning models from Google and OpenAI, you get the same issues.
Okay, we have one last question. And sorry, wanted to confirm for the previous question for Mohammed. Yeah, the fetal MRI, as Ernest said, you would need to test it, right? Because we don't really know. It was trained on MRI data for sure in the 2D, like as 2D images, but we don't know the content for fetal MRI. So just as Ernest said, you just need to test it to see what it's going to come back with. My guess is probably that's going to be a smaller portion of training data of fetal MRI, so it probably will decrease the performance. Last question from Juan Castro. Would it be worth to add some type of filter of image quality, so windowing, rotation, etc., to the model so that it won't analyze a very poorly taken image or that the outcome comes with a warning of the interpretation? Good question.
Absolutely, yes. And Dr. Anastasia can provide more comments based on my limited knowledge. There are some cases in clinical settings that you have what you have. There is no other options. I was trying to flag out some of the echocardiograms that were very poor, but then it wouldn't be clinically interesting because they said, hey, the patient is overweight. What can we do? We cannot improve the quality. So in those cases, the question becomes whether we should use the pipeline at all or not. But yes, it's amazing if we can at least gauge the uncertainty of the model or prepare some precautions.
Awesome. You know what? We have to go for lunch. But I'll just ask Anastasia. That's a great comment. Like, so if we're filtering these images going into our pipeline, you realize that afterwards, so if you train it that way, or if you know, in this case, it's pre-trained, right? And so you're filtering out these images, and so you're saying don't look at these. Then you're changing the pathway. So that's what I'm going to ask Anastasia. What do you do, Anastasia, when you get an image which you're not happy with?
So good question. We try to manipulate it as much as we can that is possible. I mean, if the patient is positioned completely not straight, you cannot change that. But with windowing, we definitely play all the time. Windowing is something that we can do on our screens.
Yeah.
Other than that, we zoom, we zoom again, but we cannot make the patient be straight. Like,
Yeah.
windowing is all we have, and zoom, I would say.
Yeah. So thank you.
We use all of it.
That's an excellent answer. So that's where, you know, when I go back to my example with ultrasound, we need the pipelines to be able to work like you or work with you. And so if we exclude images that don't meet, you know, a perfect, you know, criteria, then we're not doing what you're doing, right? Which is very interesting. And so we should really find ways to make our models more robust to do what you're doing. So meaning that you can play with the windowing, you can be more tolerant of the positioning in order to give the answer. And I'm not saying that's easy, it's not. But it is, you know, what an excellent question, because that is something to take into account. That the more you play with the input of the image, the less generalizable your model is going to be. And once again, we see, you know, how more robust the well-trained expert radiologist is, right? So there's the challenges is that, you know, Anastasia has a whole set of tools at her disposition in order to do her job. And so really we should be working towards making AI another one of those tools that she will use in order to do her job. So
The other thing
it's
I
just,
wanted to add here is that I think that someone mentioned if we have to put a disclaimer, we do add this in our report. So if the patient is rotated, we will say allowing for the patient's rotation, allowing for the technical artifact. So maybe it would be useful if the AI models could be trained to see the deficiencies of the technical problems and say, okay, I have identified this problem. So based on this is my report.
absolutely excellent. Yeah, agreed. And that is something that can be done. So that's excellent. Okay, so at this point, I'm going to say, let's have lunch.